Hello and welcome dear friends. So today we will discuss about the multiple linear regression model. In the previous lectures we have discussed about the two variable regression model where the dependent variable y depends on a single independent variable xi, and we have used OLS method to estimate the parameters, that is to get the beta 0 hat and beta 2 hat. And here we have assumed that the dependent variable y depends only on the one variable, that is xi, or we can say there is only one factor which affects the y. However, the real world is very complex. It's not so straightforward. The relationship doesn't depend only one variable, or in other way to say that there is not only one factor which could affect the dependent variable. Let us take the certain examples. Let us think about the prediction of the stock market. So, in the prediction of stock returns, if we are assuming the two variable regression model, so that we can think of that the asset return of asset I, it could depends on, let us say, beta 0 hat and plus beta 1 hat, and let us say the market return plus u hat. So here basically we are assuming that the return of any asset is the function of only the market return. However, in the real world that's not the case. There are many other factors which could affect the return of a particular asset or the particular firm. It could be the interest rate, it could be the certain characteristics of the firm which could have impact on the stock returns. So in that case, that means we have to include the other variables into this regression equation. So let us say, for example, if you are including beta 0 hat plus beta 1 hat and the market return, plus let us say that we are including the interest rate. So we are including interest rate and here u hat. In this case now it depends on more than one variable, that is not only on the market return, it also depends on the interest rate. If we have such kind of relationship where the dependent variable is the function of more than one variable, it could be two or more than two, then what we call it this multiple linear regression model. So here this is an example of multiple linear regression model. So in such cases where the dependent variable depends on more than one variable, then we will include more than one variable into the regression model. So such model is known as multiple linear regression model. Similarly, we can think of the relationship between consumption and income. So if we are assuming the relationship of the two variable regression, then we can assume that this consumption is the function of income So here we can assume the consumption is the function of income. However, we know from the macroeconomic theory, it's not the only income which affects the consumption, but the other factors such as the wealth, such as the age of the consumer, such as the society where do he lives, those are also affects the consumption behavior. So in such cases, again, we have to move to the multiple linear regression model, or we can think of the relationship between quantity demanded in the price. So primarily, if you are using this particular relationship, that means we are assuming that this quantity demanded is the function of its price. However, that's not the case. We know that the income of the consumer, then prices of other goods, or the taste and preferences of the consumers, that may also have impact on the quantity demanded. So again, in any such cases where the dependent variable is being affected by more than one variable, we have to move to the multiple linear regression model. Now, why we do include the multiple linear regression model? So why we try to include more predictor? What is the need of that? The first, by including more predicting variable, we will be able to summarize more information for the descriptive statistics. That estimated regression equation could represent the more information now. The second, it will improve the fit and the predictive power of our model. So if we have the two model where this y depends on, let us say, only one variable, beta 0 hat plus beta 1 hat and xi plus ui hat. In comparison, if we have the another model where this yi depends on beta 0 hat plus beta 2 hat, beta 1 hat xi, x1i plus beta 2 hat x2i plus ui hat. In most likely cases, this model will have more predictive power compared to this particular model, because here more information we are able to capture through one additional regressor here. Third aspect to including the more predictor comes from the fact that there are the many relationships which have the non-linearity. It is not linear relationship. So in such cases, to include the non-linearity into the regression model, we have to add the additional regressor term, for example, like this here. So once we add this additional regression, it is nothing but the multiple linear regression model. We can think of the relationship between risk and return. We do know that the return of any particular asset depends on the risk, and the relationship is not straight linear, rather than it is non-linear. So we can have risk plus beta 2 hat, then we could have risk square, and here this residual. So to incorporate the non-linearity, we have to add one additional predictor or more regressor. Similarly, we can think of the relationship between investment and the firm size. We know that the relationship between investment and the firm size could be non-linear, and we have to include the firm size here plus beta 2 hat, then the firm size square plus u hat. So again, we have to have one additional regressor. That means again, we have to move to the multiple linear regression model. The fourth aspect why we include the predictor or we need more predictor comes from the fact that there is the many relationship here. Not only the variables have effect on the dependent variable, but the interaction of these two independent variables do have also impact on the dependent variable. So in such cases, what we have here, for example, if you take this y, not only the x1 and x1 square do have x2 have impact on this y, but also the interaction between x1 and x2 do have impact on the y. So in such cases, that means again, to include this interaction term, we had to have an additional predictor regressor here. For example, we can think of the portfolio return and the risk. So the portfolio return here, it do depend on the risk. However, it also depends on the market conditions. So for example, the relationship between risk and portfolio return here, the portfolio return not only for example, the relationship between risk and portfolio return. So the portfolio return not only depends on the market risk, here, but it also depends on market conditions. So for example, we can take the relationship between portfolio return and the risk, where we can say the portfolio return not only depends on the risk, it also depends on the market condition. In addition, the risk and return, it also depends on the interaction between the risk and market conditions. So in such cases, we have to include this interaction term. To include this interaction term, that means again we have to include the more predictor. So there are the certain regions why we need to include more predictor. Now if we are including the more predictor, that means we have to move out from the two variable regression equation model and we have to use the multiple regression model. So today we are going to discuss in such cases how we will estimate the parameters and what are the properties we have of these estimates. So from here what we can observe this. So to understand that, let us say we are taking the two variable we are taking the three variable regression model where y is the dependent variable, x1 and x2 are the independent variable, or we can say the regressor or the predictors we have. So here we have dropped the subscripts to make it easier for the calculations here, assuming that the total number of observations is n. So therefore we have dropped the I subscripts representing the number of observations. So here y is the dependent variable, x1 and x2 are the independent variable, and u is the error term we have included in this model. So here the beta 0, as it was discussed in the two variable regression equation, that beta 0 is nothing but the intercept term. So basically it reflects the average value of y when both x1 and x2 are equal to 0. Beta 1 here is not the regression coefficient, rather than it's the partial regression coefficient. Why partial regression coefficient? Because the total change in y is not only reflected by x1 but it is also contributed by x2 or more other regressors. Therefore beta 1 what we know as the partial regression coefficient rather than the regression coefficient. So what it reflects? It reflects basically if there is one unit change, then the y will be changed by beta 1 unit condition upon the x2. Similarly, the beta 2 is the partial regression coefficient, and it reflects that if there is the one unit change in x2, then the y will change by the beta 2 unit conditional upon the x1. So what are the conditions we are keeping here? So in general, the condition we are assuming then, when there is the change in the x1, the x2 remains constant, and when there is the change in the x2, x1 remains constant. So the beta 1, in fact, practically it shows that if the x1 is changing by 1 unit, y will change by beta 1 unit, keeping the x2 constant. Similarly, beta 2 reflects that if x2 is changing by 1 unit, y will change by beta 2 unit, keeping the x1 constant. So that's how we interpret this model. Now, how we estimate the parameters of this? So we used again the least square, and we'll see that the least square is still a least square. That means whatever the properties, whatever the methodology we have in the two variable regression model, the same properties, same methodology here, it will remain the same intact in case of multiple regression model also. To understand that, let us take the population regression function y is equal to beta 0, beta 1 x1, beta 2 x2 plus u, and here the objective we have that we have to estimate the value of beta 0, beta 1, beta 2 using the least square method and for the sample, one particular sample. And again, like we have assumed in the two variable regression model, here we have to make the certain assumptions. So what are the assumptions we have? The first error term is the random variable. Second assumption is that expected value of random error term is equal to 0, and the variance of the error term is constant, that is the sigma square, or what we have discussed, assumption of homoscedasticity or equal variance. The fourth assumption we have, again, there is no correlation between the two error terms, or what we know as the assumption of no autocorrelation. Then we have that error term follows a normal distribution with mean 0 and variance sigma square, and we have assumed that there is no error measurement in the x1 and x2, or in generalized we can say there is no error of measurement into the explanatory variables. In addition to, we have also assumed the linearity in the parameters. The parameter doesn't have more than one power, and there is no specification error into the regression model. Then we have also assumed that x1 x2 are fixed in the repeated sampling, and there is no relation between the error terms and the independent variables or the regressors. In addition to this, in particular, the multiple regression model, we have one extra assumption, that is, there is no perfect relationship or collinearity between the regressors. So basically, this means that there is no exact linear relationship between the regressors. This assumption is popularly known as no multicollinearity. So what does basically it mean? That let us say if we have the two variables, let us say x1 and x2, and the relations between x2 and x1 could be represented by using this particular equation. So here you can observe that there is the exact linear deterministic relationship between x1 and x2. Either we take this relation or we take this relation. What does it mean? It means that if we know the value of x2, exact deterministic value we can find of for x1, or if we know the value of x1, we could find the value of x2 without any error. Exact value we can find. So if we have such kind of relationship, then we say that both these variables are perfectly collinear. So if we have such kind of variable relationship in the two variables or the regressors, we will not be able to estimate the parameters. We will see when we will discuss about the violation of assumptions. However, let us say if we have a relationship x2 is equal to x1 square, but here we will be able to use. Why we will be able to use? Because here if you see, we are assuming that there is no exact and linear relationship. So there is the emphasis on the two terms. One is the exact and another is the linear. So in these two cases, this is exact and also linear. So this is the violation of this particular assumption. However, here this is exact, however it is not a linear. So this is not the violation of this particular assumption. So given the population regression function and these assumptions, we can estimate the sample regression function of this. So let us say the sample regression function we have y is equal to beta 0 hat beta 1 hat x1 plus beta 2 hat x2 plus the residual u hat. Now what the objective is that we have to derive the OLS estimates of beta 0, beta 1 and beta 2 hat. That is, we have to estimate the beta 0 hat, beta 1 hat and beta 2 hat. So how we do that? So again we use the same principle for the OLS method. What is the principle? The principle is that we have to minimize the sum of squared of residuals, which already in detail we have discussed in the two variable regression model. So here we are not going to discuss in the detail, however briefly we will discuss those certain steps we had. So the same principle, we have to minimize this sum of squared of residuals. Why we are minimizing the squared residuals? So those things we have already discussed. And we have to minimize this with respect to the beta 0 hat, beta 1 hat and beta 2 hat. And we follow the similar steps which already we have followed into the second two variable regression model. So first we will take the partial derivative of this function, then equate it equal to 0 to obtain the first order conditions. Then we will get the normal equations, and by solving those normal equations we will get the value of this beta 0 hat, beta 1 hat and beta 2 hat in terms of our sample observations. So we will be able to get the numerical value of those estimates. So let us say here what we have, we are giving that function is this, then we have to minimize this, we will take the partial derivatives of this function and equate it equal to 0 with respect to beta 0 hat, beta 1 hat and beta 2 hat. Now once we do this, we will get the three normal equations. So those normal equations are written here. So by taking the solution of those things, we will get these three normal equations, and by solving these normal equations, we will be able to get the values of beta 0 hat, beta 1 hat and beta 2 hat. However, if we express this OLS estimators in the deviation form, it becomes easier in the calculation. So Rather than taking the absolute value here, we will rewrite it in the deviation form. So deviation form means deviation from the mean. So we are using a smaller case here. So smaller y is nothing but y minus y bar. Similarly, x1 is nothing x1 minus x bar, and x2 is nothing but x2 minus x bar. So if you are using the deviation form, then these three normal equations turns reduces to into basically two normal equations. That is, here we have these two normal equations. Now solving these two normal equations, we will be able to get the value of beta 0 hat, beta 1 hat, and beta 2 hat, and that will be like this here. So we solve these two equations, we will get the value of beta 1 hat and beta 2 hat, and using the mean equation formula we can get the value of beta 0 hat. So the beta 1 hat is nothing but the summation of xy multiplied by summation of x square minus summation of x2y, summation of x1 and x2 divided by summation of xn square, x2 square minus summation of x1 x2 whole square. If you observe carefully, the similar pattern here we are following. So instead of x1 now we have x2, and instead of x2 here we have x1 square, and instead of x2 we have x1, and this repeats as it is. Denominator we have remains the same. So using the OLS method, we will be able to estimate the value of beta 1 hat, beta 2 hat, and beta 0 hat. Now let us say what are the moments we have. That means when we are talking about the moments, that means we are talking about the mean and variance. So what is the mean of these OLS estimates we have? So these OLS estimates have the similar property, similar mean as we have done in case of two variable regression equation. So here again the expectation of beta 0 hat is nothing but the true population parameter. Expectation of beta 1 hat, that is the mean of the beta 1 hat estimate, is nothing but the true population parameter, and here also true population parameter. And already we have discussed while discussing the blue that this is known as unbiasedness. That means in case of multiple unit regression model, the OLS estimates will be also unbiased estimates. Because why it is unbiased? That expected value of the estimates will be equal to the true population parameters. Now let us turn to the variance. So the variance of OLS estimates will be given this, how the similar derivation methods we will be able to follow as we have done into the two variable regression model. Only the certain steps will be more. Similarly, the variance of beta 1 hat, we could write this, and this could be written also in the form of here variance of beta 1 hat sigma square upon summation of xi square, x1 square 1 minus r1 2 square, where r1 2 is nothing but the sample coefficient correlation between x1 and x2, which could be written like this. That is the covariance square divided by standard variance of this and variance of this. Similarly, variance of beta 2 hat we can write, and here this again r1 2 is nothing but the coefficient correlation, and the covariance between beta 1 hat and beta 2 hat could be written in this particular form. Now here we know that the unbiased estimate of the sigma square, because this is the sigma square of the population, we do not have this information. So the unbiased estimate already we have proved is nothing but the sigma hat square, which could be obtained by using the formula summation of u hat square divided by n minus 3, where n minus 3 is nothing but the degree of freedom. Here why we have 3? Because to estimate to calculate the residuals, this is u hat, which is basically this u hat is nothing but y minus beta 0 hat minus beta 1 hat and beta 2 hat x2. So that means we have to have the value of beta 0, we have to have the value of beta 1 hat, and we have to have the beta 2. Therefore, we have to estimate the beta 0, beta 1 and beta 2. That means we are losing the 3 degrees of freedom. So therefore, we have n minus 3. In general, if we have the k variables, that means in that case we have n minus k, where k is the number of parameters including constant. So These are the mean and variance of this OLS estimates in case of multiple linear regression models. Now, what are the properties we have? We will observe that the same properties we will have as we have in case of two variable regression model. So, first, the expected value of y will be equal to the expected value of estimated y. Second, the summation of residuals or the estimated error terms will be equal to 0. There will not be any correlation between the residuals and the explanatory variables, and the residuals, that is the estimated error terms, will be uncorrelated with the estimated value of y. So, these are the properties which already we have discussed in the previous lectures while discussing the two variable regression model.